Hi, and welcome back to DATQVAULT video lectures. This lecture is going to be on the free radical halogenation of alkanes. So just remember that there are review sheets for each of these lectures, and if you didn't print out the review sheet for this particular lecture, I suggest at least taking notes. That's because I think it's really important in these lectures to be an active learner. And even if you don't like particularly reviewing your written notes, it's actually proven that memory is increased dramatically if you write and listen and watch at the same time. So the mere act of writing down what I'm talking about and taking notes can really improve later retention of this material, which on a time crunch basis for studying for the DAT could be actually really helpful and important. So let's look at the halogenation of alkanes. It's definitely one of the first things you learn when you take organic chemistry, so you're very likely to see something like this on the DAT. Here I have a very simple example of halogenation of alkanes. This is methane, and you can halogenate methane using some sort of a halogen, and then if you hit these two things with UV light, and sometimes you see it activated by heat. You get usually just a monohalogenation of your alkane, and then you get a byproduct of the halogen acid. So, just as a reminder, for halogenation of alkanes, X2, so our halogens for this reaction are limited to chlorine and bromine. We usually don't see this reaction very often with fluorine, and that's because it's a highly exothermic reaction and is actually explosive. So it can be done, but it's really dangerous to do, and you usually don't see it. This reaction also is not done with iodine, and that's because the reaction itself is too endothermic. So the reaction actually doesn't go at all. So just remember that for halogenation of alkanes, you're only going to likely see chlorination and bromination. All right, so let's look at the mechanism of the halogenation of alkanes. And like I said earlier, it goes by a radical mechanism. So this is kind of an introduction also to how radical mechanisms actually work. So the first thing that happens in a radical mechanism is typically the initiation of your halide. And this is done, in this case, through UV light. So we're going to look at the halogenation of methane with chlorine. So the first step in the initiation is if you shine UV light on chlorine, then you will get homolytic cleavage of the chlorine bond. And this means one electron in this bond goes to one of the chlorine atoms, and the other electron in the bond goes to the other chlorine atom. And this is represented by drawing two separate arrows from this bond with a single prong on each arrow, which indicates the movement of only one electron. Alright, so once we get the homolytic cleavage of this chlorine-chlorine bond, we end up with two chlorine radicals. And it's these chlorine radicals that will begin to react with our methane molecule. So I have drawn out here a methane molecule, and I've accentuated one of the CH bonds because this bond is going to participate in a reaction with this chlorine radical. And again, this is going to happen through homolytic cleavage of this CH bond. So one electron from this CH bond is going to go and react with the single electron of the chlorine radical, and then the other electron in the CH bond is going to go to the carbon of the methyl group. Once this happens, we get our methane radical here, and then we also get HCl as a byproduct. So now we're going to take this methane radical, and we're going to react it with another molecule of chlorine. So this entire process after the initiation is called our propagation step. And we'll see why it's called propagation after this reaction here takes place. So we take our methyl radical, and again we will, with this methyl radical, homolytically cleave this chlorine bond, and we get out our halogenated product, and then we also get, sorry, I'm going to go back here for a second. We also get a chlorine radical as a byproduct. So the fact that we get a chlorine radical as a byproduct of the propagation of this methyl radical and another chlorine atom, we do not need to keep initiating chlorine atoms up here to create chlorine radicals. The methyl radical actually forms more chlorine radicals, which can then go back to the beginning of this propagation step and continue propagating more of these chlorine radicals, and then creating more of our halogenated product. The last step is going to be called the termination step. So once we've kind of, I guess, exhausted a lot of our chlorine, there might be more chlorine radicals in solution to react with methyl radicals. So instead of the methyl radical reacting with a chlorine atom, we can have the methyl radical react directly with the chlorine radical, since there are quite a bit of those just hanging out in our reaction solution. So if this happens, we're no longer propagating any more chlorine radicals. Instead, we're forming our halogenation product, and we're terminating both of our radicals that we have in solution. That's why it's called the termination step. The termination step can also lead to a couple different byproducts. For instance, if we have two chlorine radicals reacting with each other, we can get out one of our starting materials, which is just chlorine. And if we have two methyl radicals reacting with each other in solution, we can get out ethane, which is obviously not the product that we want because we're looking for a halogenated product. To avoid getting ethane as a byproduct, this reaction is typically run with a high excess of chlorine so that there's way more chlorine radical to react with than there will be other methyl radicals. Alright, so let's look at the stability of alkyl radicals, which is actually going to be really important later on down the road when we're looking at reacting chlorine or bromine with more molecules than just besides methane. So if you look at this chart here, we have stability increasing this way. And if we notice, the least stable alkyl radical is actually the methane radical, which is what I showed you a reaction with in the previous slide with chlorine. The more alkyl groups that you add to that central carbon that bears the radical, the more stable the radical actually is. And this occurs for the same reason as a carbocation radical. Through hyperconjugation of the hydrogens on these other alkyl groups out here, it stabilizes the radical. And this is because the structure of alkyl radicals actually looks very similar to the structure of carbocation. So here I have a radical and a carbocation. Carbocations, if we remember, just have an empty p orbital, so they're positively charged. And radicals also have this same p orbital, which makes the structure completely planar. But instead of being completely empty, the p orbital contains one electron in it. Alright, so there are a few differences between radical chlorination and radical bromination, and we'll cover those right now. So let's take this molecule right here where we have 9 primary hydrogens and we have 1 tertiary hydrogen, which is right here. So if we react this with chlorine with some UV light, we can get 1 of 2 products. We can get chlorination at this central tertiary carbon, and we can also get chlorination at one of the primary carbons. If you remember the previous slide, we know that tertiary radicals are going to be more stable than primary radicals, which we must form at least one of these during the chlorination process. But if both of them were equally as reactive, so if the primary hydrogens were as equally reactive as this tertiary hydrogen here for the chlorination, we would expect about a 9-to-1 ratio, because there's 9 primaries and 1 tertiary hydrogen, of both of these products. But that's not what we see. We actually see a 2-to-1 ratio of each of these products. And that's because tertiary hydrogens are far more reactive than primary hydrogens in chlorination. And that's because the tertiary radical is more stable than the primary radical. So we can actually determine why this percentage is the way it is, and that's because the rate of abstraction of a tertiary hydrogen is far faster than a secondary, which is faster than a primary. So if we have a primary carbon, a secondary carbon, and a tertiary carbon, the rate of abstraction is a ratio of 1 to 4 to 5. This is, for chlorination, is commonly called just the 1-4-5 rule. So let's go ahead and figure out why these percentages are the way they are. So for the top one, we have 1 carbon that is tertiary, so there's only 1 tertiary hydrogen in this molecule. The rate of abstraction is 5 times the rate of the primary carbon. We have 9 primary carbons, and the relative rate of abstraction of that primary carbon is 1. So this is 5 and this is 9. So if we total these up, that's going to be a total of 14. So just by looking at relative ratios, we have a 5 to 14 ratio here, which is 36%, and 9 to 14 is going to be 64%. So this is a way that you can easily determine the relative ratios of chlorination of a molecule that has a certain number of primary hydrogens, secondary hydrogens, and tertiary hydrogens. So let's look at the radical bromination of alkanes. It's far different than chlorination. And that's because when we do the reaction with Br2 in the same exact molecule that we used for chlorination, we get almost 100% bromination at the tertiary carbon. So this hydrogen here is abstracted far faster in bromination than it is in chlorination. And so the relative rate of abstraction of that hydrogen for bromination is 1 to 82 to 1,640. So if you remember, for chlorination, it was 1 to 4 to 5. So this means that bromination is way, way more selective for a tertiary carbon than chlorination is for a tertiary carbon. And this happens for one of a couple reasons. First of all, the bromine radical, because bromine is a larger molecule, it's more polarizable, can stabilize that radical a lot better than a chlorine can. So the bromine radical, first, is far more stable. And because of its increased stability, its reaction with an alkane radical is going to have a far lower activation energy barrier. So because of this, the reaction is going to be far less exothermic. So because the reaction is going to be less exothermic and it has a lower activation energy barrier, it's not going to react as fast, and it's going to wait around for the tertiary radical to form versus reacting super fast with either a primary or secondary radical, because the bromine radical is just far more stable. All right, so let's do a DAT style question on radical reactions with halogens and alkanes. So here the question is, what is the major product for the following reaction? So why don't you go ahead and pause the video for a second, try to figure this out, and then we'll solve it together. All right, now that you've had a second to solve this question, we'll go over it together. So the DAT is completely computerized test, so you're not going to be able to draw on the test at all. So instead you're given like kind of a whiteboard and a dry erase marker, so which is represented by this box over here. So I'm just going to draw all the answers in here. So first thing that we notice about this problem is that the molecular formula is actually in a condensed form, which makes the problem a little bit more tricky because it's harder to see bonds that way. So if anything is ever in a condensed form, I suggest drawing it out first so that you can see which carbons are primary, secondary, and tertiary, which is important for a radical reaction. So if we draw out this molecule, it's going to look, oops, sorry, I drew one too many carbons. It's going to look something like this. So remember that a radical addition of bromine to an alkane is highly selective for tertiary carbons over secondary carbons over primary carbons. So here we have a primary carbon, and a primary carbon here. Here we have a secondary carbon, and here we have a tertiary carbon. So this hydrogen is going to be the hydrogen that's abstracted the fastest, and if we replace that hydrogen with a bromine, we get this molecule right here. So we don't really need to eliminate any of these options right away. It's easiest probably just to draw out the answer, because we can quickly come to that conclusion because we should already know that tertiary carbons are going to react far faster. Tertiary hydrogens are going to be abstracted far quicker than secondary and primary ones. So if we go through and look for the proper answer, we notice that E is going to be the correct answer because the bromine is bonded directly to this tertiary carbon and has replaced the hydrogen. So just want to remind you guys that there is a lot of practice problems that you can tackle for each of these lectures. So definitely take the time to do them because a point or two can drastically improve your DAT score, and that could really make all the difference when compared to everybody else who's taking the exam. So definitely do these practice problems, do these practice exams to really solidify everything that we talked about in this lecture and all the other lectures.